Hello there, Will Patillo here, and today I would like to demonstrate for you a voxel algorithm I have been working on over the last few days. The rules for it is that voxels come in four different types: black, green, blue, and red, and they each start from a seed location, as we saw at the beginning, which defines where a voxel of each type starts and also enforces their rate of spread. So they increase at a linear rate rather than exponentially for reasons of balance that I will get to later. The voxels may spread in any direction. I've had other versions of it that are three-dimensional. This right here is two-dimensional, as that's easier to observe. They can also be of varying dimensions. So right here, I think they're roughly 3 units tall and half a unit in width and length. And all voxel types may spread into empty areas each round, but then they can also convert adjacent voxels depending on their color. So black is able to spread into green, as you can see in the bottom left and center. Green can spread into blue, as you can see in the bottom right. Blue can spread into red, as you can see at the top. And red can spread into black, as we see in the middle. Black and blue and also red and green are neutral to each other, as we can see with some of the stable points of red and green in the middle. Interestingly, one thing that has come up, I don't entirely know why, is sometimes we'll have voxels get trapped, such as the red and green at the bottom or the blue and black a moment ago, where voxels will try to enter in and then get blocked even though it seems like it should be able to spread. So I'm not entirely certain what's causing that, but I liked that behavior, so I haven't really tried to debug it at all. And the end result of all this pattern is you get this lovely kind of swirling motion. The larger the space, the more pronounced the spirals that you get. Starting with multiple seeds, as I have in the beginning of this one, obscures that a little bit at the beginning, but eventually, once it calms down, it starts to look more or less the same as having one voxel of each color at the beginning, and you get this kind of spiraling effect, which looks very nice. In the smaller settings, often after a while, it'll stop in some kind of stable state where one color has completely dominated, or maybe there's a few trapped voxels like the red one surrounded by green, surrounded by black, that you can see in a few points. But the larger the space is, the more it seems to resist stopping in some sort of stable state, where it will seem like one color is about to dominate, but just before it does, another one that is able to consume it starts spreading out. Next we see another run of the exact same underlying algorithm, but this time it's represented slightly different visually. So the blue voxels are now being represented as black. Black are still black, and the red and green voxels are now invisible. The basic dynamics of black into green, green spreads into blue, blue spreads into red, red spreads into black are still there. It just doesn't. It's just only seen as black and invisible. And this comes down to the gameplay purpose of this, which I am experimenting with. The idea right here is that the black represents a shadow or a spreading threat that's moving through the space that the player has to evade or move between, or maybe push back with some weapon that they have. Or it could be that dangerous threats like lurk inside the shadows. So for some reason, whatever reason, where the voxels, visible voxels are something that the player has to react to. And so this swirling pattern that results is going to affect the gameplay. I'm not entirely sure whether this will actually work in a real gameplay context, but it's been fun to experiment with. At the very least, it results in some interesting patterns to watch. Now, this video, of course, has been sped up significantly. In an actual gameplay scenario, the shifts would be happening at a much slower rate. Now, I mentioned earlier the use of seed voxels to enforce a linear rate of spread. The reason for that relates to player interactivity. If the shadows represent some sort of threat, then their rate of spread impacts the game difficulty, and enforcing a linear rate allows for a much greater designer control over that experience. If you are interested in seeing how all of this stuff works, including looking at the code, all of this that you see here is available on my open source project, which I will be linking to in the description below this video. Thank you very much for watching, and I will see you in the next one.